let's talk about working with power series. And the power series that we're going to start with when we're working with these is this useful power series that's coming out of the geometric series. So the series from n equals 0 to infinity of x to the n, which is just 1, plus x squared, plus x cubed, plus x to the fourth. We're centered at 0 here, and we know that this will converge to 1 over 1 minus x for all x's in absolute value less than 1. So we know that we have a radius of convergent, using our language from our previous definitions, a radius of convergence of 1, and we have an interval of convergence between -1 and 1. And this is centered at 0, and we can go to -1 and 1, and it is on that interval on the x-axis that this infinite polynomial, this power series, converges to this function 1 over 1 minus x. So we know that. So now let's use that to generate some power series and their associated radiuses of convergence and intervals of convergence for some other functions. Okay, so let's start with this function. So say we want to take the power series that we just discussed, which we know converges for absolute value of x less than 1, and we want to find a power series representation for this function. And we should say, and the associated, let's just do the radius of convergence. If we wanted the interval of convergence, we could check the endpoints. And radius of convergence. So what we're going to do here is we're going to do some algebra, some manipulation, and we're going to think, how does this function connect to 1 over 1 minus x? So what would be the connection to 1 over 1 minus x? What is the connection between these two functions? How could I rewrite this connected or in a way that looks like 1 over 1 minus x? And so here I'm looking at that x cubed right there, and I'm adding an x cubed. Well, that is the same as subtracting a negative x cubed and making a substitution. What I'm doing there is I'm actually making a substitution of negative x cubed into that function, which means I can make that same substitution into the power series. So that would be equal to, and I'm going to circle that equals real quick. I can substitute that into the power series representation for 1 over 1 minus x from n equals 0 to infinity of 1 over 1, excuse me, into the power, delete that out. All right, this is going to be equal to, I can take that negative x cubed and I can substitute that into my power series representation where I've got an x, negative x cubed to the nth from n equals 0 to infinity. But I'm going to circle that equal sign right there because that's true, right? 1 over 1 minus x is equal to the power series x to the n from n equals 0 to infinity. That is true when the absolute value of x is less than 1. So I have to remember that. I can make that connection between the function 1 over 1 minus x to its power series representation, to the infinite polynomial, but that's only true if the absolute value of x is less than 1. So when I make this substitution right here, that's why I circled that equal sign. When I make that substitution right there, I have to also add in my statement that this is true when the absolute value of negative x cubed is less than 1. So I can make that connection. I can make that equals, put a little star, and I circled that equal sign. I can make that connection as long as I also make that statement there too, which will help us with the second part of the question, which is to find the radius of convergence. So let's just continue to simplify that a little bit. That's n equals 0 to infinity. This is actually -1 to the nth and x to the 3n. And so what would that look like if we were to expand that out? Because remember, we're making a connection between a function and a polynomial, an infinite polynomial. So let's just take a look. What does that look like? Well, that means, let's see, when n is 0, this would be 1, x to the 0 is 1. Then it would be minus x to the, when n is 1, x to the third, and then plus x to the sixth, then minus x to the ninth, and plus, and so on and so forth. So what we have just done right there is we have shown that our function f of x, which is 1 over 1 plus x cubed, is actually equal to the power series from n equals 0 to infinity of negative 1 to the nth x to the 3n, or written out, the infinite polynomial 1 minus x cubed plus x to the 6th minus x to the ninth, so on and so forth. For, now we do want to simplify this a little bit. We've got negative, this is true when the absolute value of negative x cubed is less than 1. So that's simply when x cubed is less than 1, and then we can take the cube root. And so that would be, if we take the cube root of both sides here, that would be when the absolute value of x is less than 1, because the cube root of 1 is 1. Okay, so this is for the absolute value of x less than 1. And we actually have a power series representation. And because we used a known series, we actually generated not just the power series representation, but when we did it, we also figured out that the radius was 1. So again, if we want to have a little visual, what this means is, since this power series is centered at 0, that means that we have convergence between negative 1 and 1. So this function, 1 over 1 plus x cubed, will converge to this, I should say, the power series will converge to 1 over 1 plus x cubed as long as the x's are between negative 1 and 1. Now, we could actually check the two endpoints here pretty quickly. I only said radius of convergence up here, and I think I'll skip this on the next ones. But if we wanted the interval of convergence, just as a quick reminder, you just check your endpoints. So you would check at negative 1 and you would check at 1. If we plug in negative 1 into this power series, we would get a negative 1 to the nth and a negative 1 to the 3nth, which would be the power series. That would become negative 1 to the nth times negative 1 to the nth, because it would become negative 1 to the third, which is negative 1 to the nth, which is, when you multiply those together, negative 1 to the 2n, which is, of course, negative 1 squared is 1. So that is just the sum of 1, so that diverges. So it diverges at negative 1. You could check at 1 as well. If you plug in 1, you end up with negative 1 to the nth power, which also diverges. And so both of those endpoints diverge. So the interval of convergence, it turns out, is actually negative 1 to 1. And we could show that by checking the endpoints. Remember, for intervals of convergence, we have to check the endpoints after we've determined the radius of convergence. Okay, let's look at another example. Let's look at one where we take what we just did for 1 over 1 plus x cubed. And so let's just rewrite that. So note, since we just did that problem, we just showed that 1 over 1 plus x cubed was equal to the power series representation from n equals 0 to infinity of negative 1 to the n x to the 3n, which was 1 minus x cubed plus x to the 6th minus x to the ninth, and so on and so forth. So we just did that. We did that right up above, negative 1 x to the 3n. And now notice that we're taking a slight variation on that. And again, this equality right here, we can't say that without also having the statement when, for what values of x. So this is when x is less than 1. So I've got to keep that in mind. That's true. We can say this equality is true, that this function is equal to this power series as long as the absolute value of x is less than 1. Now, notice what we're doing here. We're taking that function and we're multiplying it by 3 times x to the 5th. So we're taking this function right here and we're multiplying by 3x to the 5th. 3x to the 5th. And we're taking this polynomial and we're multiplying by 3x to the 5th. That's the only difference here. That's what we're doing. And when we do that, notice what happens. Let's do it on the polynomial first. This becomes a distribution. You're just distributing that multiplication. You have to multiply, when we write that, you have to multiply every term in the polynomial by 3x to the 5th. So this becomes 3x to the 5th minus 3x to the 8th plus 3x to the 11th, and so on and so forth. We just distribute. So same thing when we work with the power series. When we take 3x to the 5th, and we already know, again, that this equality, as long as the absolute value of x is less than 1. We know that the 1 over, we know this piece, 1 over 1 plus x cubed, is equal to the power series from n equals 0 to infinity, negative 1 to the nth, x to the 3n. So what we can do right here is we can actually distribute that 3x to the 5th to all of the terms in the power series. So this becomes the sum from n equals 0 to infinity of 3. We've got an x to the 5th times negative 1 to the nth, x to the 3n. Well, x to the 5th and x to the 3n have the same base, so we can add their exponents. So, and I'm going to jump down here. So this becomes the power series. We still have that. That's just a constant 3. Every term is going to have that constant 3 when we distribute it. Negative 1 to the nth, x to the 3n plus 5, and n starts at 0, goes to infinity, and this is how the function g of x, 3x to the 5th, over 1 plus x cubed can be represented, as long as, again, with this equality, right, we can't make that equality statement for all values of x, but we can as long as the absolute value of x is less than 1. So again, remember what that's saying right there is that the radius of convergence is 1, that we're centered at 0 and we've got convergence to this infinite polynomial from negative 1 to 1. And if we were to write this out, so just to show that this will be the same as we did here with the polynomial, so we've got this polynomial right here. Uh-oh, I scribbled. We've got this polynomial right here. So let's just show that our power series that we've just done does represent that. When n equals 0, we get 3x to the 5th. When n equals 1, we get negative 3x to the 8th, and then positive 3x to the 11th, and so on and so forth. So you can see that you do get that representation of this function by this infinite polynomial, this power series. So we're able to represent that function by a power series simply by using, it was actually really a two-step problem because I subtly had us figure out the 1 over 1 plus x cubed first and then add in the multiplication by 3x to the 5th. And just a reminder there, right, we are just multiplying an infinite polynomial. That's what we're doing when we multiply that 3x to the 5th within the power series. Let's look at one more. So if we have 1 over 5 plus x squared. When I look at that, and I have to think, I'm trying to connect it back to that known series, right? I'm kind of my thought bubble here. I'm thinking, how would that connect back to the known series? 1 over 1 minus x we know is equal to the power series x to the n from n equals 0 to infinity. We know that to be true. So how do I connect this series to that known series? That's the thought process here. We're taking what we know, which is limited right now. We only know that power series for that one function, but we can play with that and work with it, and then when we get more known series, we'll be able to do the same thing. So same idea here. I'm trying to think, okay, how do I connect this guy, make it look something like 1 over 1 minus x squared? And the first thing I notice is that I could pull out a 1/5, and then that becomes 1 plus x squared over 5. And then that, of course, is 1/5 times, I'm running into my interval from above, so I'm going to erase that, 1/5 times 1 over 1 minus a negative x squared over 5. And so notice what we've got going on there. We've got a constant, so we're just multiplying a constant, and we can do a substitution. We can sub in negative x squared over 5 into my power series. So let's take that. I'm going to rewrite it down here. Let's take that h of x. So, and I would like to be in black. So let's take that function, 1 over 5 plus x squared, and that's going to be equal to, I'm going to go ahead and circle that because it's equal on a certain interval, but that's going to be equal to the power series from n equals 0 to infinity of, well, we have 1/5, let's put the 1/5 out here for now, we have 1/5 times a negative x squared over 5 to the nth power. And that is true as long as what I substituted in, negative x squared over 5, is less than 1. So we'll clean that up in just a second, but let's work on the power series first. So the power series, let's keep going there. That power series, we've got that 1/5 maybe make it a little bit bigger here. We've got that 1/5 times the power series from n equals 0 to infinity. Let's clean that up. That's negative 1 to the nth x to the 2n over 5n. And that is true when the absolute value of negative x squared over 5 is less than 1. So of course that's just the absolute value of x squared is less than 5. Multiply both sides by the absolute value of 5, which is 5. Take the absolute value of the negative 1. Then we can even take the square root. And when we take the square root, I don't need to show the index on that one. When we take the square root, the absolute value of x is less than the square root of 5. So this is going to be true, right? Again, with that equal sign, right? We can state that statement of equality as long as we've also stated when it is true. So this means that we are centered at 0 here, and this means that my interval of convergence runs from negative root 5 to positive root 5. Now, what happens at those endpoints, we could check, but we do know that the radius is the square root of 5. Okay, let's go ahead and write out a couple of terms there. And oh, actually, I want to clean one more thing up. I just caught that I'd left the constant outside. I don't really like that constant hanging outside. Remember what that constant outside of a summation means is that we're multiplying every term in the sum by 1/5. So we can bring that inside. So that's the summation from n equals 0 to infinity. Negative 1 to the nth, x to the 2n, and on the bottom we end up with 5. Because it's 5 to the first, we get 5 to the n plus 1. And if we wanted to write out a couple terms, we could do that. So when n equals 0, this would be, in the top we would just get 1, and on the bottom we'd have 5. And on the next term, we'd have a negative x squared over 5 squared, or over 25. Let's write that as 25. Over 25. And then on the next term, we'd have a positive x. So when we're plugging in 2, positive x to the 4th over and 125, and so on and so forth. So we end up with that infinite polynomial for 1 over 5 plus x squared h of x is actually equal to that infinite polynomial from n equals 0 to infinity of negative 1 to the nth, x to the 2n, all divided by 5 to the n plus 1, as long as the absolute value of x is less than root 5. So we've got another function that can be represented by an infinite polynomial as long as our x's are within root 5 of 0. So the absolute value of x is less than root 5. Okay, let's just do one more real quick. I noticed I had number 4. I think I said 3 was going to be my last one, but I'm going to do this one too. And this one I already kind of set up. That if we have 1 over 1 plus x, that's just 1 over 1 minus negative x, which of course we can write as that power series because we're thinking how does that connect to 1 over 1 minus x, which just is the power series x to the n. I'm writing this a bunch on this video so that you can see that connection because it's one of our useful power series because we can connect it to other functions and use it to build more power series. So this is a useful power series. So this is going to be equal to, notice on this one, this is a simple one because the only substitution we're doing there is we're substituting in negative x. And so this becomes negative x to the nth from n equals 0 to infinity, which of course is just negative 1, the switch, times x to the n from n equals 0 to infinity. And so this just becomes 1 minus x plus x squared minus x cubed plus so on and so forth. And this is true. Again, we can use this equality as long as the absolute value of what we're substituting in is less than 1. So as long as x is less than 1 with a radius of convergence of 1. And so we can make another statement, and this is another one that we could add into kind of our useful power series. It's easy to derive from our first useful power series, but it's also common enough that it's nice to have memorized that it is negative 1 to the nth, x to the nth, 1 minus x plus x squared minus x cubed, and so on and so forth for the absolute value of x less than 1. So this is, again, another one of those. Another useful power series. that slight variation on 1 over 1 minus x. This is 1 over 1 plus x, and we get that useful power series just with the alternating sign, with the switch on it. So that's one nice thing that we can do. Once we've created and come up with, determined a power series for a given function, then we can manipulate it if needed for that given function.